Hello guys, welcome to 9.6, our last section of the semester. So we're going to start by doing a quick review. So um, let's say we have a homogeneous system like that, right? And we know that our solution is going to look like something of this form, right? If and only if lambda and u, they are your eigenvalues, right? Lambda is an eigenvalue and u is an eigenvector. Okay, so in this section we are going to look at the case what happens when lambda is complex. Right. So when you solve the characteristic equation, usually we end up solving a polynomial. So when solving a polynomial, it's possible for us to have a complex lambda. Right. So suppose we have lambda is equal to alpha plus I beta, right? And then we go ahead and find a corresponding eigenvector that is in the form of A plus IB, right? So now that we have an eigenvalue and eigenvector, of course, we can come up with the general solution. But before we do that, remember that complex numbers, they have conjugates. That means if we find one complex eigenvalue, that means its conjugate has to be a eigenvalue as well, right? That means we can say lambda 2 is the conjugate of lambda 1, which is alpha minus I beta, okay? And similarly, for the eigenvector, right? We're going to have Z2, call it Z1, Z2, is going to be A minus IB, right? Because it's the conjugate of the first eigenvector. All right, so therefore, by doing this and combining with Euler's equation, we will get two linearly independent complex vector solution that is in the form of e to the lambda 1 t z1, and another one is e to the lambda 2t z2. Now keep in mind that lambda 1 is complex, right? So let's rewrite it as alpha plus I beta t, and then a plus ib. Okay, and similarly for the second one, right? E to the alpha minus ib t, and then a minus ib. Okay, so let's look at the first one, W1 first. We're going to rewrite this as the two products of exponential, right? Like that. Okay, and we can apply Euler's equation on this, right? Which will look like this, e to the alpha, and then e to the I beta t. We can write it as cosine beta t plus I sine beta t. And then a plus b, ib. Right? All right, so this is by Euler's equation. We can write this in terms of cosine and sine. And then if we multiply these out, we can eventually, alpha, I'm going to leave the t here. All right, so we have e to the alpha t multiplied by cosine beta t times a minus sine beta t times b and then plus I sine beta t times A plus cosine beta t times B. Okay. So this it will look like our general solution to the system. And of course we have another one, so we have to polish it a little more. All right, so let's see how we can work with just W1 for now. So I'm gonna rewrite W1 as to sum x1 plus ix2, right? Where x1 is this thing, right? And x2 is this thing, well, of course, with the e alpha t. Now, we know that x1 and x2 are a real vector solution. Okay. Now, that means that they're real, right? And we know that W1 is a solution to W1 prime is equal to AW1. Right, that's the system that we're looking at. And if we replace the original X with the W1, this is what we have. All right, and then we can keep moving, replace W1s with X1 I plus I X2, and then we have something like this, X1 prime plus I X2 prime is equal to AX1 plus IAX2. Okay, so here we have the real part and the imaginary part, right? So this part is the real part and this part is the imaginary part. So if we quit the real part, we get that x1 prime is equal to AX1, and then the imaginary part is going to be x2 prime is equal to AX2. So by looking at these two equations, we can say that x1 and x2, they are actually the real vector solutions to the original system with complex eigenvalue, right? So for these, we have the eigenvalues to be complex, which we got from earlier, alpha plus or minus I beta. Now, since they have distinct eigenvalues, then they are actually linearly independent as well. Okay, so all this is just to show you how we got to the final answer, but to put it in simple terms, right? If matrix A has complex eigenvalues, alpha plus or minus I beta with eigenvectors A plus or minus IB, then two linearly independent real vector solutions to x prime minus ax is equal to 0 are. Right. And then this is also in your notes, equation 4 and 5. X1 is e to the alpha t cosine beta t times a minus e to the alpha t sine beta t times b. And x2 is e to the alpha t sine beta ta plus e to the alpha t cosine beta t times b. Okay, so this is basically your general solution, right? If you want to find general solution, this is the form you use, and then of course you can add C1 in front of it, C2 for general case, right? But we have alpha and beta, A and B in here, right? They're both in here. The only difference is the plus and minus, and of course the first one is cosine. Here the first one is sine, and then sine and cosine. All right, so let's take a look at some examples together. All right, example 1, we want to find a general solution to the system x prime equal to ax. So find general solution. Okay, and then we started with this matrix A. Okay, so the first thing, of course, is to find the eigenvalues. So to find the eigenvalues, we find the determinant of A minus lambda I and set it equal to 0. Yeah, so go ahead and give that a try, but I'm going to show the work here in a few seconds. Okay, so first you multiply out to get the characteristic equation, and then expand it, and you get a third-degree polynomial. Go ahead and solve it. Right, and here I'm actually using the remainders theorem, so find the roots. I found that 2 is a root, and then this is my remaining polynomial, and that's a quadratic, so we can use quadratic formula to solve this. And this part actually gives me a pair of complex conjugates, 2 plus or minus I. Right, so that is our eigenvalues, so 2 and 2 plus minus I. Right, and let's move on to find eigenvectors. All right, so first we start with lambda equal to 2. We are going to look at A minus 2I. Okay. All right, so A minus 2I times this eigenvector will give us 0, right? And then this is what we have here. As you can see that the first and the third row, they are the same, right? So we just have the first and the second row to work with. Okay, so this is what we have. After I perform some elementary row operation, I clean out the third row because it's the same as the first row, and then multiply row 2 by 3 and add to row 1. All right, from here we get that what do we have? Let's say y plus z is equal to 0, and then this is negative x plus 2y plus 2z is equal to 0. All right, and then we can come up with, okay, y is equal to negative z, right? So let's say let y be 1, and then z will be negative 1. All right, plug it into the second equation. I'll get negative x plus 2 minus 2 is equal to 0. So negative x is equal to 0. X is equal to 0, right? So our first eigenvector will look like 0, 1, 1. No, 0, 1, negative 1. All right, next let's look at the first complex eigenvalue, 2 plus I. Now we actually just need to find one of them, and then the eigenvector for the conjugate of lambda 2 will be the conjugate of the eigenvector that we find here. All right, so let's do this. F A minus 2 plus I lambda u. Oh, not lambda, I times u is equal to 0. All right, so we're gonna start by exchanging row 1 and row 2 so that we get a negative 1 here, which will be easier to work with. And let's next multiply the first row by a negative 1. All right, this is what we have. And next we want to make these two terms 0. So R2 is going to be negative 3 minus I times R1, and then add to R2. And then row 3 is just going to be a negative 3R1, add to row 3. Let's see what we have. All right, this is what we have. And then let's go ahead and make that 1, right, by multiplying I over 5. And this is what we have. All right, next let's make that 0. All right, and then we have something like this, but this is very nice. If we look at the equation row 2, that actually tells us that y plus 2/5 plus 1/5 I z is equal to 0. That means y is negative 2/5 plus 1/5 I z. Okay, so if we let z be equal to 5, then y can be a little nicer, which is negative 2 plus I. Oh, minus I. Sorry. Minus I. Right? And then we can plug that into first row to get x. So x plus negative 2 plus I times y, which is negative 2 minus I. Now they are conjugate of each other, so that's easy to find. Minus 2 times 5 is equal to 0. So x plus, so conjugate, that's 4 plus 1, that's a 5, minus 10 is equal to 0. So x is equal to 5 as well. All right, so our eigenvector, complex eigenvector, will be 5, negative 2 minus I, and 5. Okay, now, to find the other eigenvector, it's very easy. Just take the conjugate of z. So just change that to a plus, and then you have the third eigenvector. All right. So let's do a recap. Okay. So here we have everything. The 3 eigenvalues and the 3 corresponding eigenvectors, and all we need to do now is just to put them in the general form. Right, so x of t. First, we have the real one, which is a little easier, right? E to the 2t multiplied by 0, 1, negative 1 plus c2. And this is where things can become a little trickier, right? So we have e to the 2t. Right? And then not 2t, 2 plus I t, and then 5 negative 2 minus I, 5 plus c3 e to the 2 minus it, 5 negative 2 plus I, 5. Right, but we don't want to include the i's in here, so we are going to use Euler's equation to rewrite those. Right, and you can look at the notes for general form. So basically we will have c2, and then first one would be 5 e to the 2t cosine t, negative 2 e to the 2t cosine t plus e to the 2t sine t, and then 5 e to the 2t cosine t. Right. And then next one, c3, that's 2 minus I, so we have first one 5 e to the 2t sine t, and then negative 2 e to the 2t sine t minus e to the 2t cosine t. All right, and the last one is 5 e to the 2t sine t. There you go. It's a very long process because this is a 3 by 3, but it's good that we're taking a look at the harder one in on the video here. It actually took me a while to get through to find out what the eigenvector is, but you know, after a few more practice, you will be fine. Okay, let's look at the next one. Okay, so example 2. I've written down a lot of work. It's a little long and quite time consuming. So I'm gonna go over this real fast. So we started with our matrix A right here, and then our goal is to find the determinant of A minus lambda I, which is right here. Okay, so to find the determinant of a 4 by 4, this is very annoying. I'm going to do the sub matrix by picking the first first column, right? So you can see that lambda, negative lambda, multiplied by the determinant of the sub matrix, which is just 3 by 3, and then minus this one I 1 multiplied by the sub matrix. All right, and you get a very long equation like this, and at the end this is your characteristic equation right here, right? And to solve this, I actually use a remainder theorem to check 1 and -1. So 1 is a root to the characteristic equation. That means 1 lambda equal to 1 is an eigenvalue, and then also -1 is also another eigenvalue. And then resulting polynomial is this, and we use quadratic formula to solve it, and then we get a complex root, which is 2 plus minus 3i, right? So we get our all of our roots, right? Lambda is plus minus 1, and then 2 plus minus 3i, right? And then we're going to use that to our advantage and try to find what our eigenvectors are. All right, so we can actually look at this in two parts, right? The first two variables and the second two variables. So right here, we actually get that, I'm gonna use it, negative x plus y is equal to 0, and then x minus y is equal to 0. So both of them say that x is equal to y, right? So we can say they are 1, something like that. Very easy. Okay, let's look at the last two. So negative z plus w is 0, and then negative 13 z plus 3w is equal to 0. All right, so here z is equal to w. All right, and then we get what? Negative 13w plus 3w is 0. Negative 10w is 0. So w is 0, and z is 0. Okay. All right, so u1 is going to be 1, 1, 0, 0. Okay, very easy. All right, so for lambda equal to -1 is pretty similar to that, right? Here we have x plus y is equal to 0. That means x is equal to -y, so maybe 1 and -1. All right, let's look at z and w. So z plus w is 0. That means z is negative w. Okay, so we have negative 13z plus 5w is equal to 0. And we have 13z, so substitute that in. 13w plus 5w is equal to 0. Right, so that gives me w is 0, which means z is 0 as well. All right, so let's see what we can do here. We can do 1, -1, 0, 0. Right, as our second eigenvector. Right, 1 and -1, or -1, 1, doesn't matter. Right, as long as these two are 0. All right, let's move on to the next one, the complex eigenvector. All right, and again, we can look at this as a 2 by 2, right? So we can have -2 minus 3i x plus y is equal to 0. So y is equal to 2 plus 3i x, and then put it in here. This is from our first row. All right, second row we have x plus -2 minus 3iy is equal to 0. And then we know y is equal to 2 plus 3ix. Right, so x plus -2 minus 3i, and then 2 plus 3i x equal to 0. All right, and then for y'all, we have x minus 4 plus 12i minus 9 times x is equal to 0. And then what is that? Let's see. I have 5x, so x plus 5x minus 12ix is equal to 0. So 6x minus 12ix is equal to 0. All right, so in order for the real part and the imaginary part to be 0, x has to be 0. Right? So 0 plus 0. That means y will have to be 0 as well. Okay. All right, now let's look at z and w. So we have -2 minus 3i w plus z is equal to 0. And again, we can write z is equal to 2 plus 3iw. All right, plug it into here. All right, so we have -13z plus 2 minus 3i w is equal to 0. Sorry, there's a mistake. It's I have to switch those variables again. All right, so that should be a z, that should be a w. So w is 2 plus 3iz. All right, that's from row 3. And row 4, here we have this, and plug in w. So we have -13z plus 2 minus 3i times w, which is 2 plus 3iz. Right? And that's a conjugate, so that's very nice. So -13z. That'll give me plus 4 plus 9, 13z is equal to 0. Right, so we get 0 equal to 0. That means we can pick z to be anything. And again, we want to pick the easy one. So pick z equal to 1. Then w is going to be 2 plus 3i. All right, so our first complex eigenvector would look like 0, 0, 2 plus 3. Oh, z first, so z, and then 2 plus 3i. Right, and then z2 is just a conjugate of that. Right, so 0, 0, 1, 2 minus 3i. All right, now we're almost there. All right, so let's look at the real one first. So that's very easy, just e to the lambda t multiplied by this one. That will give you the first column, and then the second one, e to the lambda t multiplied by the eigenvector to get the second one. Now, for the complex one, they are a little more complicated. We have to use the general form. All right, so this is the general form I was talking about, right? Using your alpha and beta, and also the vectors a and b to find the general form. All right, so for this one, we will have e to the alpha t, so e to the 2t cosine beta, which is 3t, multiplied by a, that is 0, 0, 1, 2, the real part, and then minus e to the 2t sine 3t multiplied by the imaginary part, 0, 0, 0, 3. Okay, so that's all for this one, and let's work on the last one. That is e to the 2t sine beta, so 3t times a, 0, 0, 1, 2, plus e to the 2t cosine 3t times b, so 0, 0, 0, 3. All right, now to put everything together, I'm gonna squeeze it down here. You know what? Let me open a new page. All right, so here is our fundamental matrix. E to the t, 0, 0, And then second one, e to the negative t multiplied by the vector. So e to the negative t and negative e to the negative t 0, 0. All right, and the third one, so we have 0, 0, and then here we have e to the 2t cosine 3t, and the last one we have e to the 2t cosine 3t, and so 2, and then minus 3e to the 2t sine 3t. Okay, that's all in the third column, right? And the fourth column, we have 0, 0, e to the 2t sine 3t. And then the last one, we have 2 e to the 2 e to the 2t sine 3t plus 3 e to the 2t cosine 3t. All right, there you go. That's it. Now it might take a while to understand what's going on here, but all we're doing is following the general form and looking at each entry and what that is. All right, example 3, we want to solve this, and given two initial conditions, x of 0 is -2 to -1, and then the other initial conditions, x of -pi is 0, 1, 1. All right, so let's start by identifying the matrix, right? Okay, and then find its eigenvalue. Right. All right, so find the determinant, and then we get the characteristic equation. When you use solve this quadratic part using quadratic formula, we get 1 plus or minus I. All right, so we have a real eigenvalue and a pair of complex eigenvalues. All right, so first let's look at lambda equal to 2 and try to solve the augmented matrix. So just fill in the numbers, 1, 0, -1. Right, 0, 0, 0. All right, so here we have negative x minus z is 0, and x minus z is 0, right? So the only case for this to be true is when both of them are equal to 0. That means y is free. All right, so we can just say, oh, not question mark, y is free, right? So let y be equal to 1, right? So u is 0, 1, 0. All right, now next for lambda, our first complex, lambda is 1 plus I, so we want to find 1 minus 1 plus I is equal to 0, and here it is. All right, here we have it. All right, so we're gonna do something similar, trying to solve this. All right, so I'm gonna multiply row 1 by I. All right, that'll give me positive 1, 0, negative I, 0, 0, 1 minus I is 0, 0, 1, 0, minus I, 0, like that. All right, so if you look at the first and the third, right, we both get that x minus iz is equal to 0. And then we have 1 minus I times y is equal to 0. All right, so here we know that x is equal to iz, right? So if z is 1, x will be I, right? And here, the only case to make this a 0 is a 0, right? So our first complex vector would be I, 0, and 1. All right, and z2 will just be the conjugate of that, negative I, 0, 1. All right, let's see. So first, we have 0, 1, 0, and z1 is I01, and then Z2 is negative I01, right? Whereas the lambda here is 2, and this is 1 plus I, this is 1 minus I. All right, and let's put them in journal form. Okay. Right, so here is our general solution, right? And next, all we need to do is plug in the initial value and then try to solve for C1, C2, and C3. All right, but let me clean this up a little bit and put it in the next page. Okay, so here we have it. Right, and this form is a little nicer to, a little better to look at. All right, and then let's plug in our initial value. X of 0 is -2 to -1. All right, and let's see. X of 0 will be C1, 0, 1, 0 plus C2. And that's a 1, that's a 0, 1, and 1. Right, so 1 plus C3 to -1 and 1, so -1, 0, 0. All right, and that's equal to what? -2 to -1. All right, so from here we can see that C1 takes care of the middle one, so C1 is 2. C2 is the last one, so C2 is -1, and C3 is the first one, so negative C3 is -2. That means C3 is 2. All right, so that's put in as our final form. All right, so we have 2 e to the 2t. Right, make it a little bigger. All right, the first one only gives us the middle term, so this is 2e to the 2t. And then C2 is -1. So here we have e to the t sine t, and then negative e to the t cosine t. And C3 is a 2, right? So multiply in there. So -2e to the t cosine t. It's a 0, don't worry about it. And then plus 2e to the t sine t. Okay, and there we go. That's our solution for the first part, for the first initial condition. All right, now let's look at part B, the second initial condition, which is negative. X of negative pi is equal to 0, 1, 1. Okay, so x of negative pi will give me, let's see, C1, 0 e to the -2 pi, 0 plus C2. So pi, that's 0, 0, 0, negative pi, that is -1. So negative e to the negative pi plus C3, 0, right? Negative pi, -1. So that's positive e to the negative pi. And that is equal to 0, 1, 1. All right, so 0 from here, C3, this has to be 0, so C3 has to be 0, right? And then we have C1 e to the -2 pi is 1. That means C1 is e to the 2 pi. And C2 negative e, C2 e to the -pi is also 1. So C2 is negative e to the pi. Okay. All right, so let's see what we have here. Let me get a little more space. I'm gonna erase that. So x of t will be equal to, first, C1 e to the t, right? So that will be negative e to the 2 pi plus t. All right, and C3 is 0, so we don't have to worry about this part. Sorry, I made a mistake. Sorry. All right, so C1 is e to the 2 pi. All right, so e to the 2 pi times e to the negative 2 pi give us 1 here. All right, and then C2. Oh gosh, what am I doing? So e to the 2 pi, put it here. We get e to the 2 pi plus 2t. And then C2. So C3 is 0, so we don't have to worry about this part. C2 is negative e to the pi. Put it here. So that's e to the t minus pi sine t. And the same thing here. That will give me negative e to the t plus pi. Oh, plus pi, my bad. Plus pi. And then cosine t. Whew. So that's a very annoying problem right here. Now, I know this question can be a little annoying, but don't worry, take your time. Try it on your own, and you will see that it's actually very similar to what we've been doing, but just in this case that we have complex eigenvalue and complex eigenvectors. Yeah, feel free to drop by to my office hour if you have any question. Thank you very much, and that'll be all for today.